Hey everyone, welcome back to linear algebra. This will be part B of lecture 4. And so we've been discussing matrix multiplication. Now we just went through a nice lengthy theorem about some of the properties of matrix multiplication. So the associative property in particular we saw holds, and we also saw the distributive law holds. Some things do not work though. Some of the things that you may naively sort of associate with real number multiplication does not work with matrix multiplication. So one of those things that we should talk about is cancellation laws. Cancellation laws, it's kind of a loosely termed cancellation laws. Some people don't refer to them as laws, really just something else, but the cancellation laws do not hold for matrix multiplication in general. Right, so what we kind of expect is that A times B, if A times B equals A times C, then the cancellation law is this idea that, hey, I can cancel an A from both sides and I get that B is equal to C. So this does not imply that B is equal to C, however, in the case of matrix multiplication. Right, sometimes it's true for sure, but not generally. Generally, it is not true. Okay, so let's see an example here. Let's see an example. Okay, we'll just do some kind of smaller matrices here. 2, 1, 6, 3 for A. B will let be -1, 0, 5, 2. And C we'll say is 3, 1, -3, 0. Okay, and so we just need to calculate AB, calculate AC. We can clearly see that B and C are not equal, right? But we can multiply A and B together and A and C together, and we'll see that they are equal. Right, so AB is 2163 times -1, 0, 5, 2. Right, and so when we do this product, we get -2 plus 5, 0 plus 2, -6 plus, so hold on, so plus 15, and then 0 plus 6, right? So just kind of doing the multiplication here. And so we get 3, 2, 9, 6 for AB. Okay. And when we do AC, again, it looks similar here, but 3, 1, -3, 0, right? Obviously, C is a totally different matrix than B, right? But when we do the multiplication, we get 6 minus 3, 18 minus 9, 2 plus 0, and 6 plus 0. Okay, and so when we multiply, and we kind of simplify all of this, you'll see that you get 3, 2, 9, and 6 again. Right, so that shows us that AB is equal to AC. Right, but obviously B is not equal to C. Right, here's B, here's C. They're not the same, but we just showed that AB times AC is the same. So this is the cancellation law being kind of, this is a specific example where it doesn't hold. Right, in general it doesn't hold. Okay, so that's the cancellation laws do not hold for matrix multiplication. They hold for real numbers, but not matrix multiplication. Okay. And it's not hard to kind of see why, right? Like this sum is obviously does not work the same as a single digit compared, right? So you've got kind of two things going on here. Right? So if you dig into this a second, you can kind of see where the cancellation law kind of falls away here. Another one that is kind of taken for granted is the following. It is also not necessarily true that if AB equals 0, that A equals the 0 matrix or B equals the 0 matrix. Okay, so that's not necessarily true. Like in general, when we talk about real numbers, if two real numbers multiplied together give you 0, then we say that one of them has to be 0. But not true for matrices. Right? Let's see an example of this as well. Here we'll let A equal 2163 again, and then we'll let B equal -1, 2, 2, -4. Right, and so when we multiply AB together, what do we get? Well, we've got -2 plus 2, okay, and then we've, right, so -2 plus 2, and then we've got -6 plus 6, and then 4 minus 4, and then 12 minus 12. Okay, and so we can see that the product AB is 0, but A is non-zero and B is also non-zero. Right, so AB is equal to the 2 by 2 0 matrix, but A is not equal to the 2 by 2 0 matrix, and B is not equal to the 2 by 2 0 matrix either. Okay. All right, so that's another one that we can't take for granted, right? We have to be careful when we're reasoning about matrix multiplication to not abuse the idea of the cancellation law or of the zero-sum law, right? Zero product law, sorry. Okay, all right, very good. Let's talk about exponents of matrices and matrix powers. Okay, so let's define this. Let's let A be any n by n matrix, so square matrices now, right? So remember, square matrices are the only kind of matrices that we can multiply with themselves, right? Because they have to have the same number of rows and columns. In order for the order to work, the flipping of the order to work, the matrix has to have the same rows and columns. And in the case of flipping with yourself, obviously your rows and columns must be the same, right? So that's what's happening here. So let A be any n by n matrix. Then the non-negative powers of A are given by, well, so you've got A to the 0 power, and we define that to be the identity matrix, the n by n identity matrix. A1, A to the first power is just A. Okay, and for k greater than or equal to 2, we say A to the k power is just equal to whatever A to the k minus 1 power is times A. Fairly easy to understand. Okay, so we define A to the 0 to be the identity. A to the first power is obviously just A, and then A to the second power would be A to the first power times A, so A times A, and so on, right? So you got A to the 0 is equal to the identity. A to the 1 is equal to A. A squared is equal to A to the 1 times A. A cubed is equal to A squared times A, and so on, right? So you can see here I define these two and then I get everything else, right? Sort of recursively defined. Let's do an example here. I mean, it's a straightforward idea. We just kind of need this for some of the proofs. And it's also like, it's nice to start with just defining the first two and then everything else being kind of recursively defined. So based on the previous ones. Right, so if a is equal to 2, 1, negative 4, 3, then a squared is equal to a times a, which is, again, 2, 1, negative 4, 3, times 2, 1, negative 4, 3, right? And so I've done this ahead of time, and this is 0, 5, negative 20, and 5, right? And you can do that multiplication to confirm that. So that's a squared. Then a cubed, what's a cubed? Well, it's just a squared times a, right? So again, it's 0, 5, negative 20, and 5. That's a squared. And let's just multiply it times a again. Right, and so then I'd get something else. So negative 20, 15, negative 60, and 5, negative 5. Right, and you can confirm that again. Right, and so I could keep going and say a to the fourth is a cubed times a, right? So it's recursively defined. Okay. All right, very good. So that's the idea behind exponents of matrix exponentiation like that. Now, what about, here's another example. IN, we talked about this, I think when we introduced matrices, we discussed the identity matrix. So IN is basically an n by n matrix with 1 on the main diagonal and the rest zeros. Right, and it'll have n rows, n calls. Okay, and so the identity matrix, it's called the identity matrix, obviously for lots of a couple of reasons. One of the reasons is that if I square the identity matrix, so here I'm taking I2, right? So I know that that's I2 times I2, which, let's write the actual matrix. Now it's 1, 0, 0, 1 times 1, 0, 0, 1. Now what happens when I multiply these together? Well, let's see, right? So the first entry would be 1 times 1 is 1 plus 0. So I get a 1. The second entry in the first row is going to be 1 times 0 is 0 plus 0 times 1 is 0. So I get a 0. What about the 2, 1 entry? Well, 1 times 0 is 0 plus 0 times 1 is 0. Right? And then you can see that for the 2, 2 entry, you're going to get 1 times 0 is 0. Oh, sorry. 0 times 0 is 0. 1 times 1 is 1. Right? So I squared, I2 squared is the same as I2. And I2, if I cube it, that's going to be I2 squared times I2, which we know is 1001 times 1001, which is going to be 1001 again, right? And so kind of like with real numbers, when we talk about 1 raised to any power is always 1, it's the same idea with identity matrices, right? In general, you know, if I'm dealing with the nth identity matrix raised to the kth power, it's equal to the nth identity matrix, right? For all k. Okay, so that's nice, right? That's very it has a lot of, it's a lot in common with the ideas that we're used to from you know, the ideas that we're used to from regular real number multiplication. Okay, very good. let's talk through another theorem here. Okay, and so this is going to be kind of a theorem related to exponents of matrices. So if A is a square matrix, and if S and T are non-negative integers, okay, non-negative integers, then first thing, A to the power S plus T is equal to A to the S power times A to the T power. Okay, so this is the familiar, one of the familiar properties of exponents that we're used to for reasoning about real numbers. And then the other one is A to the raised to the S power, and then additionally raised to the T power is equal to A to the S T, right? So you'd multiply the exponents together, and you can change the order as well. A to the T power raised to the S power. Right? So this is another one that is familiar to us from dealing with real numbers. Okay, let's prove the first one. This is a little bit of a tricky proof in the sense that it's a proof by induction, right? And so I'll assume that people have had some experience with induction proofs, maybe not a ton, so we'll kind of take it slow, but I'll have to assume that you've seen an induction proof before. So let's prove one, namely that A to the S plus T is equal to A to the S, A to the T. Okay, so with induction, we want to start with a base case. So this is actually really easy to prove using induction. So we'll start with the base case. S equals 1 and T equals 1. And we'll show that it's true for S equals 1 and T equals 1. So A to the S plus T, in this case, is equal to A to the 1 plus 1, which is equal to A squared, right? Just adding the exponents, they're just real number, or they're integers, so we can add them together. Okay, and so we can see that this is, in the case of S and T both equal to 1, this is equal to A squared. And so that's this side. What about the other side? So A to the S times A to the T, well, that's equal to A to the 1 times A to the 1, which we know is A squared as well. That's just A times A squared. Okay, and so these two together show that for S equals 1 and T equals 1, A to the 1 plus 1 equals A to the 1, A to the 1, right? So as you would expect, that's the base case. Okay, now let's assume that this relationship holds for some S and T and consider the next instance. So assume that A to the S plus T equals A to the S, A to the T for some S and T, right? Where S is greater than or equal to 1 and or T is greater than or equal to 1. Okay, for some S and T, and let's consider S plus T plus 1. Let's consider the next one, adding one more. What happens? Let's see that the fact that it's true for S and T implies that it's true for S and T plus 1. Okay, so easy enough to do. Let's say we'll start with A raised to the S plus T plus 1 power. Right? Now this is going to be equal to A raised to the S plus T plus 1 power. Now what am I doing here? Well, this is just associativity, right, of integer addition. These are just integers. I'm associating them. Okay, and we know that this is going to be equal to A raised to the S plus T power times A. Now, why is that true? Well, that is the definition of powers for matrix multiplication, right? That just comes from the previous definition. Okay, and next we can see that this is going to be equal to A to the S times A to the T times A. Now, what am I doing here? How did this happen? Well, this is the induction assumption, right? Specifically this thing here, right? We showed it's true for s equals 1 and t equals 1, and then we assume it's true for some other s and t, and we're going to show that that implies it's true for s plus t plus 1 more. Okay, so that's the induction assumption. Okay, and so we'll keep cruising here. And the next thing is, what can we do with this? Well, we can reassociate it, right? We know that associativity works. And that's just associativity. And it's like matrix multiplication associativity. We had a theorem earlier in the section on that. Okay. And then finally, we can say this is a to the s times a to the t plus 1. Now, what is this? This, again, is the definition of powers for matrix multiplication. A to the t times a is equal to a to the t plus 1. Okay, and what have we shown? We've shown that this is equal to this, which is exactly what we needed to show. Okay, and so because the induction relationship holds, we can say this is true for all st non-negative integers. For all s and t that are in z plus, or non-negative, maybe that's easier to say. Okay, so that is that. Perfect. All right, so kind of a trickier proof, especially if you're not familiar with induction, but it's actually fairly straightforward if you are familiar with induction. Okay, now so that's those are the familiar properties of exponents. One of the properties where we kind of left off, though. So a property that does not hold is this one. You may remember, if I have a product of real numbers and I exponentiate the product, that's the same thing as exponentiating the first number and then exponentiating the second number. Now, in the case of matrices, this is not true. So in general, this does not hold, and so we say in general it's not true. Okay, so let's see an example of that, a counterexample where that fails. So we'll let a equal 2, -413, and b equal 3, 2, -1, 5. Then I'm just going to kind of do this. I have it all written out already. Actually, I did these already. So a times b, if I multiply these together, and you can confirm this, just pause the video and double check that you get the same answer. 10, -16, 0, and 17. Okay, so that's a times b. And then if I exponentiate this, I get, like, maybe we'll take this, we'll square it. If I square this, I get the number 100. And then -432, and then 0 and 289. All right, so that's ab squared. What's a squared? Well, that's just taking this matrix and squaring it, and what I end up with is 0, -20, 5 and 5, and b squared. If I square that separately, I get 7, 16, -8 and 23. Again, pause the video and confirm those products. And so then a squared plus b squared, or a squared times b squared, sorry. Now, if this property were true, we would expect a squared times b squared to equal this, but in fact it does not. And you can easily confirm this by doing the product yourself. I'll just write it out. We get this matrix instead. Okay, so these are not equal. right? So in this case, AB quantity squared does not equal A squared times B squared. Okay. And it's true for all powers. AB to the nth power is not necessarily equal A to the n, B to the n. All right, very good. Very, very good. Okay, and I think we have one more theorem, and that is this guy for this section anyway. So one more theorem. If A is an m by n matrix and B is an n by p matrix, okay, then what? Well, A times B transpose is equal to B transpose A transpose. That's kind of an unusual result, right? So if I multiply two matrices together, A and B, and then I transpose the product, it yields the same result as transposing B, transposing A, and then multiplying those two matrices together in the reverse order. Okay, so that's something that's a little bit surprising at first. Okay, we won't prove this one. It is one that you could prove, and I'll just say the way you'd want to approach it would be to consider the ij entry and the dimensions again. So first show that the two matrices have the same dimensions, which is really easy, and then show that the ij entries are the same. Now, when you talk about the ij entries, you can be kind of conversational in this for this proof, I think. You don't have to be as formal as the previous proof where we had to denote the ij entry. I think you can be a little more informal. It's a little bit convoluted, but it's relatively straightforward. But it is kind of an unusual thing to see when you first see it, that the transpose of a product reverses the order of a product. That's interesting. Okay, let's see an example of this, and then we'll call it quits for today. We'll start with a matrix 2, negative 4, 1, 3. And B, that's our matrix A, and B will be 3, 2, negative 1, 5. Well, we can multiply A and B together, and we will get 10, negative 16, 0, and 17. And then AB transpose is just transposing the rows and columns. So 10, 0, the first column becomes the first row, and the second column becomes the second row. Okay, so that's that. And what we can show is that B transpose A transpose in this case is equal to this product. And so B transpose would be 3, negative 1, 2, 5. So again, making the first column into the first row. And then A transpose would be 2, 1, negative 4, 3. Right, and when you multiply those two matrices together, you get 10, 0, negative 16, and 17. Again, pause and confirm. Right, but you can see that that is obviously equal to this result here, which is AB transpose, right? So this is just an example. This is obviously not a proof, but it kind of can be used to maybe show you a little bit of how the proof might work, right? If you kind of go through and think about what's being multiplied with what, da 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 da, it can help you reason about the ij entry part of the proof of the previous theorem. All right, very good. So that's matrix multiplication, kind of a longer section, probably going to be the most complex fundamental operation you've ever done from algebra. But with some practice, you can get fairly good at it fairly quickly. So just give it some practice, give it some time. Next time we get together, we'll jump into section 2, and we're going to start learning how to solve systems and some interesting techniques that can be applied to matrices that represent systems. Until then, take care, keep at it, and practice matrix multiplication. It's something that you'll never get good at until you just do about 20 or 30 of them, and then you're like, okay, I get it. So practice away, and we'll talk to you next time. Take care.